Welcome to The Explainer. Today, we're digging into something I find absolutely fascinating about the history of science. We often think of scientific laws as these unbreakable rules, right? Well, today, we're going to explore how exceptions to those rules aren't actually failures at all. Instead, they're super exciting clues that point us toward hidden realities. If you're the kind of person who loves a good intellectual mystery, you are definitely in the right place.
Okay, let's dive into this. Have you ever wondered what exactly happens when a perfectly formed, flawless diamond completely shatters an elegant, highly respected 19th century scientific rule? Just refuses to follow it. It turns out, when matter rebels like this, it's usually trying to teach us something entirely new.
Section 1. The Dulong-Petit Gamble. To really understand the rule that diamond broke, we need to jump back to the year 1819. This brings us to our two protagonists. First, we have Pierre-Louis Dulong, a hardcore experimentalist who actually lost an eye and a couple of fingers to his explosive chemistry work, and teaming up with him is Alexis Thérèse Petit, this brilliant young physics prodigy.
Now, at the time, scientists were hitting a wall trying to figure out how different elements absorb heat. If you just compare a gram of carbon to a gram of lead, the results are a total mess. But Dulong and Petit had a major breakthrough. They realized that comparing equal masses was totally muddying the waters. It was mixing up two very different facts: how many atoms are actually in that sample and how much thermal response belongs to each individual atom. So, they decided to switch things up. Instead of doing the accounting by mass, they did it by atomic weight, effectively comparing equal numbers of atoms.
And this brilliantly illustrates their findings. When you look at the raw data, lead and iron have vastly different specific heats. But watch the visceral math happen here. When you multiply lead's super low specific heat by its high atomic weight, you get a value of about 0.37. And then when you multiply iron's high specific heat by its low atomic weight, boom, you also get about 0.37. In fact, 13 different elements magically clustered right around this exact same common value.
To put that into modern terms, this rule means that almost all solid elements require the exact same amount of added energy to raise their temperature. We measure this as about 25 joules per mole per Kelvin, often just represented as 3R. Because they were finally comparing comparable amounts of atoms, looking at moles rather than grams, the thermal behavior of all these wildly different solids suddenly just aligned perfectly.
Section 2. Diamond breaks the law. So this elegant, bold wager seemed to organize the elements perfectly. It was a massive, game-changing triumph for early 19th century science. That is, of course, until they measured a diamond. Because diamond simply refused to play along.
Here is the spectacular plot twist. Diamond's molar heat capacity at room temperature isn't 25. It's only 6.1 joules per mole per Kelvin. That is roughly 1/4 of what everyone expected. It spectacularly failed the established law. And it wasn't some silly error like comparing masses instead of atoms. They were already doing the math right. Diamond was just inexplicably wrong.
So the crucial point is understanding exactly why it behaves this way. Diamond is essentially carbon arranged in an exceptionally stiff, rigid, three-dimensional network. Because these bonds are locked in so incredibly tight, the solid just doesn't absorb heat in the classical way at room temperature. Its atomic vibrations are highly constrained.
But the story doesn't end there, not by a long shot. Fast forward to the 1870s, and an experimentalist named Heinrich Friedrich Weber decided to track how diamond reacts across different temperatures. The data he found is wild. Near room temperature, it sits at that weirdly low 6.1, but when he heated it up to 800 Kelvin, it jumped to 19.5. And by 1100 Kelvin, it reached 22.5. It gradually climbs right up toward that classic Dulong-Petit limit of 25. This completely shifted the scientific question from, why is diamond wrong, to what happens when it gets hot?
The answer actually lies in a tiny mathematical tug-of-war. On top of the equation, you have the energy cost to make the atoms vibrate, which is dictated by the stiffness of the bonds and Planck's constant. On the bottom, you have the actual thermal energy available from the temperature. Because diamond's bonds are so notoriously stiff, the energy cost to vibrate is pushed way, way up. At room temperature, there simply isn't enough thermal energy to unlock it. The environment is just too cold to wake up those stiff vibrations.
Section 3. Faraday's wrong-way solid. To really cement our understanding of how these broken laws teach us new physics, let's look at a parallel case. Enter Michael Faraday. He was a former bookbinder's apprentice with very limited formal schooling, who somehow became one of history's absolute most brilliant experimentalists.
Faraday found another material acting completely in reverse. You know, the familiar rule of thumb for ordinary metals is that heating them up agitates their atoms, scattering the charge and increasing electrical resistance. But in 1833, Faraday discovered that a solid called silver sulfide actually conducts electricity better when it's heated. It literally did the exact opposite of what the laws of conduction said it should do. Faraday was incredibly hands-on and practically minded. He fused a piece of silver sulfide in a glass tube, inserted platinum wires into opposite ends, and cranked up the power from a battery. Because of how he set the whole shebang up, the electrical current itself warmed the sample. And this created a fascinating feedback loop. The higher temperature raised the conductivity, which allowed larger currents to flow, which produced even more heat.
What makes Faraday so legendary is his relentless experimental discipline. He didn't just throw out a strange result because it broke the rules. He distrusted his first surfaces, he endlessly varied his conditions, and he meticulously wrote down the troublesome data. He realized that warming the solid wasn't merely shaking the atoms around, it was actually unlocking new mobile charge carriers that just weren't available at lower temperatures. The heating was literally changing the hidden mechanisms of the material itself.
Section 4. Matter Maps, Hidden Regimes. Let's move to and see how this builds into our final conclusion. Both the diamond that stubbornly refused to absorb heat at room temperature and the silver sulfide that conducted electricity backward are teaching us the exact same lesson about the nature of science.
When a scientific law breaks, it doesn't mean the law is useless. The Dulong-Petit law wasn't completely wrong. It was just a high-temperature destination. Laws belong to stated conditions. These supposed anomalies are immensely valuable because they reveal missing scales or hidden energy mechanisms. Scientific laws aren't universal dogmas that apply perfectly everywhere. Rather, they're maps of specific regimes, and matter itself shows us exactly where the borders of those regimes lie.
Which leaves us with a pretty fascinating final thought. We rely on so many fundamental rules in science today to understand our universe. But if our greatest scientific laws are only true under certain conditions, within specific regimes, what invisible boundaries are we crossing right now without even realizing it? The edges of our current knowledge aren't failures, they are just maps pointing us to the next hidden regime. Keep questioning the anomalies out there, and thank you so much for joining me for this explainer.